Alrighty, well, thank you everyone for coming out. It's great to be able to talk to you today. So like Dwayne said, I'm a maintainer of Pandas, Dask. I work at Anaconda, so I'm in a very fortunate position of being able to get paid to work on open source. I am very grateful for that. So today, talking about scalable machine learning. The first half of the talk, just to kind of set things up, I want to recognize that there's more to machine learning than just making a Scikit-Learn estimator and passing it some data. There's a whole lot that goes before that and after that. So before you even set out to do anything, you should really be talking to the stakeholders, asking what they're actually trying to accomplish, understand the problem, what the solutions might look like. Then you kind of get into the more technical things, which we'll be talking about today. So how do you connect to your data source? How do you get that into a place where you can actually analyze it, do some exploratory analysis using IPython and Jupyter or whatever, RStudio. Once you've gotten a feel for the data set, know where all the bodies are buried, why this person named Null has so many observations, you're going to be doing some data cleaning, maybe using pandas. And then you're ready to finally actually do the machine learning, which may or may not need to be scaled up to larger data sets or larger problems. So those are the things that we're going to be talking about today. And then after that, you have all the headaches around deployment, reporting, sharing with your collaborators. That's something that Anaconda Enterprise can make a lot nicer. So we'll be focusing on the middle 4 or 5 items here. Alrighty. So this is a slide that you may have seen by now from Jake Vanderplas, last year's PyCon keynote, really just laying out how fortunate we are as users of Python. We have this wonderful ecosystem of tools that have been built up over many, many years. And it's really remarkable, all the progress that has been made over the past 10, 20 years or so. However, there's a bit of a problem with most of the libraries on that slide is that they don't scale out well to larger problems. So whether that's really big models that you're trying to fit, or that's very large data sets, for the most part, libraries like NumPy, pandas, they're essentially limited to a single CPU core and to data sets that fit in memory. That's where Dask comes in. So Dask wants to take the existing Python ecosystem, take libraries like NumPy, pandas, Scikit-Learn, and scale them out to the larger problems. So it really is about parallelizing the existing ecosystem, all of those libraries that you saw on that slide, and making them work well for larger problems. So at a high level, I wonder who in the room has used Dask before? Decent, good, okay. Hopefully by next week, everyone will have used Dask, but at a high level, as a user of Dask, you're probably going to run into things like parallel pandas and Dask array, which gives large NumPy array-like things. So these are high-level interfaces. You get to work with data like you would with pandas. Perhaps you've already been using pandas, and it's been working well for smaller data sets, but now you want to scale it out to a data set that's larger than RAM. In this case, you could use something like Dask DataFrame to scale your analysis out to that larger data set, and Dask will take care of operating on it in parallel. And so libraries like Dask Array and Dask DataFrame, these are built on top of the technology that's at the heart of Dask, which is the high-performance task scheduling. And this is a really flexible approach to parallelizing libraries. And that's what's enabling Dask to be able to take all of those rich libraries that we saw on that slide and parallelize them. We get to reuse all of the things that NumPy and pandas are great for. They're great in-memory computation engines, containers for data, but again, they are in memory. So Dask is going to reuse that in-memory portion and scale it out to larger data sets. So again, still at the high level here, we have Dask DataFrame. In this case, we'll read from S3. So we're reading in a bunch of CSV files in this case, and then doing a very standard pandas operation. So we'll group by, we're selecting columns, we're taking averages. Very, very regular pandas code there. And then internally, a Dask data frame is made up of a bunch of pandas data frames that are partitioned along some index. So when you actually go to do the computation, so this group by mean, when that mean is actually computing, that is using the real pandas mean to do all of the actual in-memory computations. Like Dwayne said, I'm a pandas maintainer as well, so I'm very interested in keeping the APIs the same between Dask and pandas. So this gives you a very familiar feeling data frame from Dask, only the execution is different since it's happening in parallel, but it is using pandas for those parallel operations. Same thing for NumPy. We have the Dask array. This is a distributed or parallel NumPy array. We have operations like dot, transpose, reductions along an axis. Similar sort of thing where a Dask array is made up of many smaller NumPy arrays. And when you go to do operations in memory, everything is just using NumPy at that point. And again, at the lower level, the thing that's actually powering all this is this task scheduling that I mentioned. This does a few things. First of all, we get cool slides for presentations. So this is in every Dask talk, but it's a grid search over a whole bunch of hyperparameters. And nodes that are in blue are tasks that have been completed and released from memory. Nodes that are in red are tasks that are currently held in memory and because they're needed for a later task. And you can see the scheduler. So when you do an operation like dask array.transpose, that instead of executing immediately like it would for NumPy, builds up a task graph like this, and you eventually ask for it later on with a compute method. And so when that compute method is called, it gets handed over to the scheduler, which is responsible for executing it in parallel. Dask will scale down to laptop, so you can analyze a data set in parallel on your laptop using all of your CPU cores, or Dask will scale up to large clusters of machines. And I think we'll do a demo now. So first of all, we'll take a look at the New York City taxi cab data set, and we'll use Dask to analyze that. So ahead of time, Matt Rocklin, Dask developer, set up a cluster of machines. So we have, we're going to connect to that here with our client. And we have a cluster with 50 workers and 160 gigs of memory in distributed memory. Is that visible in the back, hopefully? I'll say yes. OK. So we're going to read from, in this case, Google Cloud Storage, similar to S3, a whole bunch of Parquet files. This is the New York City taxi cab data set. I'll kick that off. And then on the right-hand side, we have the distributed scheduler UI. And this will eventually, you'll see, there's some previous computations here. That's what that is. But now we have the actual read Parquet happening on the cluster. So each of these individual vertical bars here is one of the workers, one of the 50 workers on our cluster that are doing the actual computation. And so we're reading a whole bunch of Parquet files in parallel right now. And each of those individual read Parquet files are just using pandas read Parquet underneath. And at this point, we have a Dask data frame, which, like I mentioned, is very similar, feels like a pandas data frame, only it's parallel and partitioned along the index. So we can do operations like a sum of all the passenger counts. So how many passengers traveled in New York City over this time span. If you're just doing pandas, you would use just the df.passengerCount.sum. As you can see, this is not the result, right? This is a delayed result, and you actually have to ask for it with compute, and this will kick off some computes over here. We have many small sums, so you can think of an aggregate sum as doing many small intermediate sums on the small pandas data frames that are inside the Dask data frame, transfer those small sums over to a single worker, and do a final grand total at the end. So that's a relatively simple thing to distribute. We can also do more interesting things. So in this case, we'll make do a resample operation. So we're resampling to a daily frequency, computing the variance. We can also do things like compute the tip fraction by the week and the hour of the day. Okay, so we'll filter out a few operations. This is very standard pandas things. We will filter out taxi rides that were free, essentially. And then compute the tip fraction, which will be the amount divided by the total amount, the tip amount by the total fare. We'll group by the hour, select the tip fraction, compute the mean. This kicks off a whole bunch of different computations, and we eventually get our result, which we can plot. And we notice that New Yorkers are generous in the early hours of the morning. So that is that. So I showed off Dask data frame there, which is a large pandas data frame. Similar sort of thing for dask array. Okay, so that's kind of the high-level goal of Dask, is we want to take the existing Python ecosystem, libraries like NumPy, pandas, Scikit-Learn, scale them out to larger data sets. It's not limited to those libraries, so Xarray, if people have used that, are using Dask internally to parallelize their operations. Scikit-Image is looking into it as well, so you can take your own custom code, or other libraries are looking into using Dask to parallelize internally. Or, like I said, you can parallelize your own custom code to make it Dask aware, I guess. All right, so now for the title of the talk, Scalable Machine Learning. So this is mostly packaged up in a library called dask-ml. You can install it from PyPI or Anaconda, and it's up on GitHub, so you can view all the source and everything. Kind of collecting some things that are useful for scaling machine learning out to larger problems. The way I like to think about it is kind of there's two dimensions that you might want to scale along. So along the vertical dimension, we have larger models. You can think of this as really big ensembles of models or doing big hyperparameter optimization. That'd be a large model. And then along the other axis, you have large data sets. Large here is relative to the size of your machine. So if you have you can always, you can often get a bigger machine, rent one from Amazon or whatever, to do your training, in which case the size of your data is just relative to your RAM. Scikit-Learn occupies a really important space here. It's a fantastic library for doing in-memory machine learning on models that aren't too big. And again, that's relative to the size of your machine. So you can get single node machines with tons and tons of cores. It's just a matter of what you're willing to pay. Okay, so Scikit-Learn, like I said, is great at what it does, but we do have people that run into larger problems. If you want to fit a large model, again using Scikit-Learn, you can use distributed Scikit-Learn, and I'll show that off next. But this is a way of taking a regular Scikit-Learn model and using a cluster to do the training instead of a single machine. And this works out really well. And on the other side of things, if you're looking to scale out to larger data sets, there are various approaches, and we'll see a few of these. So first we want to talk about distributed Scikit-Learn, which is scaling up in the vertical direction here. The basic idea is to use Scikit-Learn's parallelism. You have that familiar in-jobs keyword, and basically make that in-jobs refer to all of the cores on your cluster. Brief bit of background on how Scikit-Learn works internally. This is more not super useful as a user, but just to understand what's going on. When you fit a model that has some parallelism in the algorithm, so in this case, we'll take a look at random forest classifier. That's made up of a whole bunch of decision trees, in this case, 200 decision trees. Fitting each one of those trees is completely independent of every other one. So it's just a big for loop inside of the random forest classifier algorithm. What the joblib Scikit-Learn developers do is they reach that for loop and they say, hey, I can run this in parallel. And they use a library called joblib. It's bundled with Scikit-Learn. It's co-developed with Scikit-Learn. And this is what lets them do that big for loop, that loop over all the trees in parallel. You just specify, as a user, you specify in jobs equal 4 cores or -1 for all of the cores on my machine. This works really well for single machine parallelism. But if you do have even bigger models that would just take way too long for a single machine, you might want to use a cluster to do the training, in which case you can use joblib and dask. So dask has done a bit of work internally to talk to joblib. We've worked with the Scikit-Learn and joblib developers to make sure this works smoothly. And with a relatively small change in your code, you're able to take that in jobs, which previously -1 meant the 8 cores on my laptop. Now this -1 would mean the 50, 100, whatever, 1,000 number of cores that are on my cluster. As far as specifying the model goes, everything's identical. It's just a Scikit-Learn model. The only thing you need to do is change the fit call to make sure it happens inside this parallel backend. At that point, joblib and dask will be talking to each other so that the parallel calls, so in this case fitting each tree, happens on the cluster instead of on your local machine. So let's take a look at that. Restart this. Okay, so we're going to connect again to the same cluster with the 50 workers here. And we're going to make a small random NumPy array here. So this is just 1,000 by 20. It's a small data set. So we're scaling vertically along my little diagram there. And the idea is we're going to do a large grid search here, not too large, just so that finishes quickly. But we're going to be searching over a whole bunch of hyperparameters here using a support vector classifier, doesn't really matter. And then the grid search CV is also doing some parallelism here. It's got the 5 cross-validation splits. If you're just using Scikit-Learn, you'd call grid search.fit, and it would take a little while to finish, but it would finish eventually. If you want to finish it more quickly, you can use the cluster. So in this case, we're doing it in the parallel backend, and then we go ahead and fit it, just like we would. I'll rerun this so you can see it happen again. You can see the various tasks here. Each one of these, in this case, is fitting a specific hyperparameter combination on some CV split of the data set. So I want to stress that this is really just a Scikit-Learn model here. This grid search is identical to what you would have gotten if you had just run fit in not on the cluster, just using a single machine, so you can inspect the results and all that. You can do prediction, scoring, just like you would normally. At this point, this is identical to the grid search you would have gotten from Scikit-Learn. The only difference is it trained faster because we used our cluster. So the caveats here is this is using Scikit-Learn. So yeah, I'm beating it to death, but this really is a Scikit-Learn model that we're training. And Scikit-Learn is limited to, for the most part, to data sets that fit in RAM. So the caveat there is that your data set is going to be shipped to each of your workers. It has to fit in RAM. And shipping that to each worker takes some time. You have to send it across the network, which is a bit slower than copying it between processes. So you should make sure that you have enough parallelism, you have a large enough model, essentially, that it is worthwhile, which if you're using a cluster, then you probably do have a large model to fit. Otherwise, you just use a single machine, which Scikit-Learn is great at. All right, so that's distributed Scikit-Learn. That's how you would scale out to larger models. When you're perfectly happy with Scikit-Learn, it trains, it's just going too slowly. All right, so the other arm here would, I guess, be larger data sets. So what do you do in that case? First of all, I would say, do you know for a fact that you need your entire data set? Sampling is a useful technique for some problems. I would say most problems. In my experience, it works out quite well. A good way to validate that sampling is an option is to plot a learning curve. So the Scikit-Learn docs show this. Very briefly, this is showing the performance. In green is on the cross-validation set. So how well is your model doing at predicting new data? And as a function, so along the x-axis here, we have the number of training examples. So we're sampling subsets of the data. And for this specific model, naive Bayes is a very simple model. It really doesn't benefit for having more than about 1,200 examples here. Okay? So depending on your model, depending on your problem, sampling may be an option. For other cases, it definitely isn't. So check your learning curve first. If your learning curve showed that your sampling is just fine, seeing additional examples isn't helping out your classifier or your regressor at all, but you still want to do some large-scale processing of the entire data set. Say you want to score everyone in your universe for whatever problem you're working on. You want to get some probability of them being a good candidate. In that case, you can use this little wrapper from dask-ml. It's extremely simple, but the basic idea is training is identical to before. You're still just using Scikit-Learn to train on a small NumPy array. Nothing special there. You can do it using distributed joblib to do the training on the cluster if you want, but it's still just a small NumPy array. And then you come along with your entire data set. So in this case, we'll read the CSVs from S3 using dask to read them in parallel onto the cluster, and then do all the prediction in parallel using all of the workers of the cluster. If you tried to do this without the wrapper, as soon as you pass that that large dask data frame to just a regular non-wrapped SVC, it would read it all into memory on a single machine and probably crash. But if you want to do the parallel prediction, transform, whatever, you can go ahead and take a look at parallels post-bit. Personally, this would have solved all of the big data problems I faced at my last job. So if that's useful, check it out. Okay, for the people where that's not an option, where they actually need to train on the entire data set because their learning curve is still increasing, every little bit of performance really matters for their business. And then in that case, we do have a few other options. So dask-ml is implementing estimators, various estimators that are scalable in nature, something that Scikit-Learn was less concerned about when it was designed because Dask wasn't around. There wasn't a large array that you can work with in memory. So dask-ml is implementing scalable versions of algorithms that you would find in other libraries. Just a quick example here, we have spectral clustering. This is useful for remote sensing. So in this case, it's an example for some Landsat data on the right. Looking at the runtime here, you can see Scikit-Learn is in blue and dask-ml is in orange, and it really isn't a fair comparison. This is a biased benchmark. Scikit-Learn uses a completely different algorithm, a completely different implementation that is as an intermediate stage. It allocates a huge array of every pairwise distance. It does not scale well to large data sets. dask-ml uses an approximation to avoid that big array, which means that you can feed it Dask arrays, and the computation will all happen on the cluster, and everything works nicely without crashing your process, which is good. On the right, you can see this for some Landsat data of a river and some forest outside Reading, and you can see it does well. So it is an approximate algorithm, but the clustering on the left is the actual image from the Landsat. On the right is the labels that were assigned by the cluster. Something for this, like a Landsat, I forget, this was like 5,000 by 5,000 pixels. And so when you do all the reshaping and do all the pairwise combinations, it blows up into a really big matrix. But the algorithm that we implement in dask-ml is able to handle that. We've implemented some. It's a newer library, so we haven't done everything Scikit-Learn has done. We're not going to do everything Scikit-Learn has done, but we've done some of the most notable ones. And then if you have ones that you would like to see implemented, definitely come talk to me, and I'll try and ask you to write a pull request implementing it. It is open source after all. So let's take a look at Kmeans here. So again, in the same notebook. We're going to use dask delayed. I mentioned you can parallelize existing code to, if you have some custom algorithm or whatever that you want to be parallelized. In this case, we're parallelizing Scikit-Learn datasets .make blobs. So we're going to make a big Dask array that's distributed on the cluster. This isn't too interesting, but it's a quick example of showing how you can take some custom thing that's not Dask aware, wrap it with this delayed decorator, which is cool, and then build up this large Dask array without ever having to materialize it on a single machine. So we're going to make a 20 gig NumPy array 20 gig Dask array in distributed memory, and you'll see it start to pile up here. So we have there are some other data sets in memory on the cluster here, but all of these bars are just creating the random values on the workers. Okay, so at this point, we have big Dask array, and we're going to use dask-ml Kmeans. This is the two big differences here are that it works on Dask arrays without pulling them into memory. So if you used Scikit-Learn Kmeans and passed it this big Dask array, it would read it into convert it into a NumPy array and crash your machine. Dask will avoid that. And it also uses a different initialization algorithm called Kmeans parallel. It's just more friendly to being distributed. So we're going to see some communication here and the various, it's an iterative algorithm, so you'll see that kind of show up in the task scheduler here. And it'll finish here in a couple of seconds. A bit about what's going on. So we have like the pairwise distances argmin. That's finding the distance from each point to the closest neighbor. That's the E step of Kmeans. From each point to the closest cluster center. And then it says, okay, of all of those people, of all those points closest to the center, what's the new average? So your classic EM part of Kmeans, if you're familiar with the algorithm. If not, you can just use it. That's totally fine too. At this point, there will be some slight differences. So this is re-implemented from scratch. With Scikit-Learn, the labels underscore would be the labels that were assigned by clustering, and that would be a NumPy array. This is a somewhat large dask array, so we don't want to crash your worker's memory or your client's memory. So instead of materializing that large NumPy array, we keep it as a dask array, so that's still distributed in memory. But you can treat it, you do normal NumPy operations, we'll slice out a subset of the observations and then plot them here. So this is a re-implementation of Kmeans in dask-ml, but we are following the Scikit-Learn API. So as far as using it, you can just swap out the imports. And we've done a decent amount of things, I think. Definitely the lowest hanging fruit we've picked. So things like preprocessing are relatively easy to do in distributed mode. Dimensionality reduction is very useful, so PCA, truncated SVD. If you have a large data set with a ton of features, you might want to use Dask to reduce the number of features using your cluster, at which point maybe it'll fit in memory. So that can be useful as well. Again, stressing the familiarity, dask-ml estimators, they really are Scikit-Learn estimators. We subclass Scikit-Learn space estimators, so they are. Pipelines, we just reuse Scikit-Learn pipeline. There's no dask-ml pipeline. I think that's really important. It's continuing the theme of scaling the existing ecosystem, so we're working with the Scikit-Learn developers to make this as painless as possible. This is a somewhat complex pipeline. If you haven't used pipelines before, they're a way of chaining together transformations from raw data to the final estimator at the end. I'm going to color code it by their source, by what library they're coming from. So in this case, make pipeline, function transformer, that's coming from Scikit-Learn. So make pipeline creates a pipeline, and that really is a Scikit-Learn pipeline. We can write custom transformers. These can take dask arrays, dask data frames, NumPy, pandas data frames without a problem. You can also use all of the dask-ml estimators. We follow the Scikit-Learn API. Anything that uses the Scikit-Learn API can go in here. So we work well with the existing ecosystem there. Finally, Scikit-Learn's not the only game in town. I really like it, but there are other systems like XGBoost and TensorFlow. They already have distributed modes, so I think XGBoost calls it Rabbit. There's some way of doing training on distributed data sets with XGBoost. So we have systems, little imports, utilities that can help you use these libraries distributed modes along with Dask. So we're kind of taking these two distributed systems and making them work well together. So in this case, we'll import dask-ml.xgboost. This provides an xgboost.train, just like the regular XGBoost library. Only it's familiar, it knows how to work with dask data frames, dask arrays, so that you're able to do training on a distributed cluster without having to bring things through a central machine, essentially. So in that case, it doesn't make sense to re-implement all the great work that XGBoost has done. It's an amazing library. But we do want to make sure that Dask works well with it. Similar story for TensorFlow. Alrighty, so to wrap up, Dask is, again, working well with the existing ecosystem. We want to take this ecosystem and parallelize it, scale that out to larger data sets. Dask itself, I was showing off all of the fancy distributed stuff because it has a nice dashboard, it looks cool. Dask scales down to laptops as well. So if you want to use a laptop, analyze tens of gigabytes of data using just a laptop, Dask will be able to read the bits and pieces in from memory. It'll just take a bit longer. And then again, a familiar API. We're reusing Scikit-Learn, NumPy, pandas for what they're great at. So we're going to follow their APIs and then reuse them for their in-memory computation. Last little bit, I would say, is check out our brand new landing page where you can see all of the documentation, links to all the docs. You can open up Binder notebooks. This will kick off it'll build you a little Dask cluster running somewhere on wherever Binder is running, so that you can go ahead and try out Dask without actually having to install it. Although it is pure Python, so just conda install it. It's not that hard. So, alrighty, I think that is it. Any questions?